Friday, in our lesson, we explored 3 different ways to find the derivative of an inverse function. So I'm just going through with you quickly each of those 3 methods again. So the first method was if you are given an equation y equals f of x. And that equation is something that you can easily find the inverse of. Then you can find its inverse by changing x and y, taking the derivative of that new function, so getting dy dx, and then plugging in the given point. You're plugging in the x value because that functions as the y value, because in the inverses, domain and range switch. In our notes, I actually did this method second. So in our notes, this is kind of like method number 2. So if you were given, let's say, for example, g of x and f of x, where f of f represents the inverse of itself. So f of x is equal to x cubed minus 1. So what you do is say, okay, y equals x cubed minus 1. I'm going to flip x and y. Solving for y, I get g of x equals the cube root of x plus 1. So again, this is the inverse of the original. So this is like the old way of doing it. You would find your inverse and then take the derivative of your inverse and plug in your value. Again, you guys don't have these notes. I'm just walking through review. If you want to write them down on the back of a paper, you can. The back of the big thick packet's blank. But again, these are not notes you have. This is just me going through potential examples to kind of reiterate what we did. Then we also talked about finding the inverse where we don't solve for y, where we differentiated those sides and used implicit differentiation. We solved for dy dx, we got our expression in terms of y, and then we plugged in the y value needed. So that would be like this example here, f of x equals x cubed plus 2x plus 1. And you want to find the derivative of the inverse at x equals 1. So again, this is the original. So here, once I flip x and y, that turns this into the inverse. So here's my inverse derivative using implicit. So if I want to find the inverse derivative at x equals 1, that x equals 1 is really like y equals 1 in a way, or finding my y value by plugging that x value in to the original. So 1 cubed plus 2 plus 1 plus 1 gives 1 plus 2 plus 1, which is 4. So then you plug your 4 in. 4 squared, 16. 16 times 3, 48, plus 2 is 50. Okay, and then the method we learned first, which is the definition of the derivative of an inverse function using a formula. So that formula is that 1 over f prime of f inverse. So f inverse of x at that point. And then finding your values. So, for example, if you had the function f of x equals x cubed plus 2x squared plus 1, and we want to let g of x equal f inverse, where g of 2 is equal to negative 1, find the value of g prime of 2. Well, the reason I need this is because that's going to represent what I plug into the bottom of my formula. So finding g prime of 2 when g is f inverse is really like finding 1 over f prime of negative 1. So it's like finding the derivative of the y value of the inverse. So you take the y value of the original, and that's how you find the inverse of that. So you put, if this is point P, then this is your Q. Okay, and then example 6. So here we have a table. And on that table it says, let f be a differentiable and increasing function. Selected values of f and its derivative are given in the table above. If g is the inverse of f, what is the value of g prime? So again, you want to follow that same idea. G prime of 6 is equal to 1 over f prime of 3, because if you go to the original function at 6, it's 3. And again, that 6 is the y. Done. Okay, so G and F are inverses, right? So if we're looking for G prime of 6, that 6 represents the y value of F, because they're inverses. So this is the y value of F. So that would be, you're looking in this area right here. So here's where F is 6 as its y value. So that means it relates to 3. So that's why you do 1 over F prime of 3. What? You thought it was the 21? Okay, yeah, because you were treating this as the x value. But this, for this case, this is the x value of the inverse, which is the y value of the original. Again, that's kind of why we're reviewing these, so you can see more and more of those examples, because these are tricky. You have to remember, this isn't the x value, it's the y value. And they purposely, on the AP test, would give you that number 6 twice. The only saving grace would be that if you really thought it was this 6, when you went to go 1 over f prime of 21, there's no 21 that matches to plug in. See, there's even their little hint that working with the formula can be challenging for students. You just have to keep reminding them visually and showing them that the relationship between the points of a function is inverse. That's why we use the y value of the function in our formula. So I keep reiterating it is the y value. Again, I know this is challenging. I know this is something that takes a couple shots at seeing. That's why we're going to go over your homework. I actually did all of your homework by hand and recorded it so that we could watch it back, and I can kind of talk you through some of the problems, and then I'll also post that video so you can watch back anything you need to watch back. Tomorrow, you're going to do a few different online sources with short little video segments, so maybe seeing or hearing it from a different perspective will help as well. Okay, so go ahead, take out that homework and take a minute to check this. So for part A, you got 4. For part B, you got negative x over the square root of 25 minus x squared. And then for part C, you got negative 4/3. Number 2 was letter E. A majority of the inverse questions on the AP exam will be multiple choice. They will be set up very similar to numbers 2 and 3, in which they give you a function, they give you points on that function, and then they ask you to create the relationship between them. The other way you'll see inverses would be with a table. And if they gave you the table, then more than likely it would be part of a free response in which you have multiple parts to that table. Number 3, your final answer was 1/6. Okay. And again, anything that you need to see more workforce, it will be posted as a video. Okay, and then for this example here, it says using the table below, if H inverse is the inverse of H, write an equation for the line tangent to the graph at x equals 3. So again, we're looking for H inverse at x equals 3, so it's like saying H inverse of 3. I know that that's equal to 1 because this is kind of like the y value of H. So I can go to my table, I look at the y value of H, and I see that it is equal to 1. So again, this is the inverse, so it's the flip of the original. The original would have been H of 1 equals 3. So the inverse is 3 equals 1. So if you want to find the derivative of that inverse, so H inverse prime of 3 is equal to 1 over H prime of 1. So the answer here is what we find its derivative of in the denominator. So that's 1/5. And again, that 1/5 represents the slope of the inverse. So the equation of your tangent line is y minus y1 equals 1/5 x minus 3 . And then in 5, that's kind of like your chain rule. So it's f of g of x equals x. So they told you the composites were equal to the identity. That tells me they're inverses of each other. That is literally the definition of the inverse that we also discussed. So f of 1 equals -5 gives f prime of 1 equals 2/5. So what is g prime of -5? Well, that's like the y value of f. So that's like 1 over f prime of its x value, which is 1. So that's where you get 1 over f prime of 1, or 1 over 2/7, which is 7/2. All starting to come together a little bit better. And then here are the final answers to this worksheet. And if you need to see any of the work, I also have that. But sometimes I think seeing all of the work can be a bit overwhelming. So here are your answers to 1 and 2. Three, 4, 5, and 6. And 7 and 8. So again, the ones I thought were the trickiest were probably those in the middle. And just because you have to take your time and really look at them and evaluate. So like something like number 5, where you had to flip-flop because it said by using the theorem up above. So you flipped your x and y, solved for y, and got f inverse prime x equals 2x over -2, which is equal to -x. And it kind of bothered me on their answer key that they left it as -2x over 2, because the 2's cancel and it becomes -x. And again, here is some of the work for 6. So again, flipping x and y, solving, and then plugging into that formula. So that's a lot like the very first method I described at the beginning of class today. So oftentimes they're not going to specify what method you have to use, and nor will I. It's more a matter of preference. So you have all 3 of those methods, and you can pick any of the 3 you like that works for you. There are definite times where one method is more productive than the other. So for example, back on the first page of this homework assignment, on this question right here, part C and B. That's using the method 1. For the heck of it, I thought, oh, okay, I'll do this problem using the second method from our notes, just to kind of compare them. And I found that as I was doing that method 2 was getting messier and messier and messier, and it took me almost a full page to go through the second method and all of the work that we did for B and C here. So like B and C here, using that other method, took me almost a full sheet of paper. So there is definitely a right and a wrong method for certain problems, but as you can see, both methods will get you to that same answer, because both ways I ended up getting that -4/3. So just something to keep in mind. Okay, so now that you have the notes packets, in them we are going to look at a couple more multiple choice derivative type questions today. So go ahead and open it up to derivatives of inverse functions. So, if f of 4 equals 2, so that's my original, and f prime of 4 equals 3/2, and g of x is the inverse function to f of x, find the equation of the tangent line to g of x at x equals 2. So go ahead, take a minute, read through that problem on your own, and write down what you believe the slope of the tangent line is for this equation. So let's start with finding the slope of the tangent line. So, what I did in order to find the slope of the tangent line personally was looked at this and said, okay, what point am I finding the equation of the tangent line at? So it says find the equation of the tangent line to g of x at x equals 2. Well, g is the inverse of f, which means g of 2 is equal to 4. Because g and f are inverses of each other. So again, what that means is f of g of x equals g of f of x equals x, because they're inverses of each other. So the y value of f is the x value of g, and vice versa. So now I need g prime of 2, which, if you go back to our formula, that's the same as 1 over f prime of 4. So g prime of 2 is the same as 1 over f prime of 4. So f prime of 4 is 3/2. 1 over 3/2 would be its reciprocal, which is 2/3. So the slope of the tangent line is 2/3. To get the equation of the tangent line, we're going to use our new slope and the point. And I'm not using the point of f, I'm using the point from G. So again, I'm not using the point of f, I'm using the point of G. Which means the equation of my tangent line is y minus 4 equals 2/3 x minus 2. Number 2. Suppose that the tangent line to y equals g of x at -3, 5 passes through the point 2, -4. Find g of -3, g prime of -3, and the equation to the tangent line at y equals g of x for the point -3, 5. So, we're given the point -3, 5. That's kind of like saying g of -3 equals 5. We are told that the tangent line also passes through a second point. So we're told that the tangent line passes through -3, 5 as well as 2, -4. So if a line passes through 2 points, I can use those 2 points to find slope. So g prime of -3 is the slope of the tangent that passes through the 2 points, 2, -4 and -3, 5. So it's y2 minus y1 over x2 minus x1. So I get a slope of -9/5. And again, that slope would represent the derivative at -3. And then it says write the equation of that tangent line. So that would be like y minus 5 equals -9/5 x minus a minus, which is a positive 3. Okay, let g of x equal x cubed plus x plus 1. If h is the inverse function of g, then find h prime of 3. So again, h is the inverse of g. Find h prime of 3. So again, what that's saying is, when does this original function equal 3? Because if h and g are inverses at h prime of 3, that's like saying g of x equals 3. So we get 0 equals x cubed plus x minus 2. So in order to make this 0, I know that the values of x can be plus or minus 1, plus or minus 2. Those are my potential values of x based on the rational root theorem, which says factors of the last and factors of the first being divided to each other. So factors of the last are 1 and 2. The first is 1. And again, I can look at this and say, okay, 1 plus 1 is 2. 2 minus 2 is 0. So at x equals 1, I'm going to get 0. So what that tells me is g of 1 is equal to 3, and h of 3 is equal to 1. So again, g of 1 is equal to 3, so h of 3 is equal to 1. So that means g prime of x which is 3x squared plus 1. We would need to find, since they're inverses, and I'm looking for h prime of 3, that would be equal to 1 over g prime of its inverse, which is 1. So g prime of 1 is 4. So h prime of 3 is 1/4. And again, you can even see these two values are reciprocals. These two values, way up at the beginning, reciprocals. So we're seeing this pattern of reciprocals occurring with our slopes. Okay, let's take a moment to pause. Okay, I'm going to start with a very, very bold statement. None of the basic trig functions have an inverse. None of the basic trig functions have an inverse. The reason for that is because none of the basic trig functions are one-to-one. And if you go back to what we learned in the very beginning about trig functions, they have to be one-to-one. What we do in order to give the trig functions an inverse is restrict their domain, which in turn restricts the range, which creates a one-to-one function. So what we do is trick the trig functions into having inverses by restricting their domains and ranges. So if you look down at the bottom of that page, you have 6 little graphs that now represent the inverse trig functions. Okay? So, what we're going to do for the remainder of class today is look at inverse trig functions using the unit circle. So again, we determined that none of the 6 basic trig functions have an inverse. They only have an inverse on a restricted domain. And that restricted domain is going to adjust our solution set area. So if you recall, previously you learned about arc sine, arc cosine, arc tangent, which meant that that was like finding the unit circle value and then going back and telling me what angle it occurred at. The arcs only live in 3 of the 4 quadrants. So you can only get arc sine, arc cosine, and arc tangent from 3 of the 4 quadrants. So if you want to make note, arc sine and arc tan come from quadrants 1 and 4. So arc sine and arc tan come from quadrants 1 and 4. Arc cosine comes from quadrants 1 and 2. Arc cosine comes from quadrants 1 and 2. So in letter A, if you're asking for arc sine of negative 1/2, we know that the sine is negative in 2 quadrants. Sine is negative in quadrants 3 and 4. But because of our rule that arc sine can only come from quadrants 1 or 2, arc sine is equal to negative 1/2 when theta is equal to or in quadrant 4 and is 11 pi 6. So our answer to letter A, whoops, oh, I clicked a totally different slide, is 11 pi 6. So you should get a radian answer for these values. So again, you could do that on a graphing calculator. The problem with doing this on a graphing calculator is our graphing calculator isn't going to give us that 11 pi over 6. So if you did it on your graphing calculator, then what you would see is like the decimal variation of that. Letter B, arc cosine of 0. So again, what this is saying is when does the cosine of theta equal 0? So the cosine is 0 up here at the top, which is pi halves. So again, the cosine is 0 at pi halves. So cosine of pi halves would equal 0. Arctan of root 3. So again, this is like saying, okay, when on the unit circle is the tangent root 3? Well, tangent is sine over cosine. So we need when sine is root 3 over 2 and cosine is 1/2. And that occurs at pi thirds. And then letter D, arcsine of 0.3. That is not a unit circle value, so that's where you go to your graphing calculator. So on your graphing calculator, that's where you want to make sure you're in radians. You did second sine, because arc sine is the same as sine inverse. You'd plug in 0.3, hit enter, and we get 0.3046. So again, roughly, that's in quadrant 1, because pi halves is the end of quadrant 1, which is 1.57. And just in case you didn't know, pi fourths is 0.78. So this is smaller than pi fourths, but greater, well, better not say that too quickly. Yeah, it's actually even smaller than pi 6. So again, your answer is 0.3046. And if you wanted, you could go up to 9, but again, you need 3 decimals, so the 6 is a safe decimal. You need 3, so 6 is safe. Yes?
Could you just multiply by pi to get the fraction?
Like to find...
Because if you multiply, like, say it's pi over 2, and you multiply whatever the fraction is by pi every 1/2, it would be pi over 2. Does that make sense?
So you want me to take 0.3046?
I was just asking if you could do that or not.
The only problem you would get is you'd basically want to put, you'd be dividing by pi, because that's already in terms of pi. Like that 0.3046 is like a fraction times pi. So if you wanted to get what the fraction is, you would divide it by pi.
Okay.
Yeah.
That's what I didn't know if you did or not. That's what I was asking.
You can. It's not going to be a pretty fraction though.
Yeah.
Like you're still probably going to end up with a decimal, because it's repeating and non-terminal and all, like both of them are gross. But yes, you could get an approximate idea.
Okay.
I just had to like think about what you were asking me backwards. I was like, yeah. Okay. And then finding the exact value of the trigonometric inverse. So again, find the exact value, draw a picture to determine the situation. So now you have 2 trig functions at once. You have tan inverse of 3/4, and then you want to find the sine of the tan inverse of 3/4. So we're kind of using SOHCAHTOA for these problems. You got to go back to right triangle trig. And the idea is that if you have tan inverse of 3/4, that's kind of like the same as saying the tangent of theta equals 3/4. And we know that tangent is opposite over adjacent. So if you drew yourself a triangle, you could put theta anywhere you want. We know that opposite has to be 3, adjacent has to be 4. If opposite and adjacent are 3 and 4, what's my hypotenuse? 5. Excellent. So 3, 4, 5. So if the tan inverse of 3/4, well, that's kind of like saying it's equal to theta. So this is really like saying, okay, what's the sine of theta? And we know that the sine of theta is opposite over hypotenuse, or 3/5. Same with example B, inverse sine of 1/3. is kind of like saying sine theta equals 1/3. So what is my theta? So this is like secant theta. So draw your triangle. Sine is opposite over hypotenuse. So 1/3. So we need adjacent, which would be the square root of 3 squared minus 1 squared, because it's Pythagorean theorem. So 3 squared is 9. 9 minus 1 is 8. So adjacent is the square root of 8. So secant theta, well, cosine is adjacent over hypotenuse. So secant is its reciprocal. So it would be hypotenuse, which is 3, over adjacent, which is root 8. If this were a multiple choice question, they're never going to leave the square root of 8 in the denominator. So it would look like 3 square roots of 8 over 8, because you'd multiply by root 8 over root 8. So we're going to stop there. You're going to use the remainder of class time to work through more examples like this, as well as some more inverse trig derivative examples. So if you turn in that notes packet, let's flip-flop that. Well, I wanted my document camera. Okay. If you turn in that notes packet that I gave you, it should kind of look like, I gotta find your, here's a blank one. This. So it's 3.8 derivatives and trig inverses homework. So you're doing some multiple choice. Oh wait. Do not do numbers 1 or 2. Skip those. You don't know how to do those yet. You're doing the remainder, which is finding the trig stuff. So skip 1 and 2, because you don't know how to find the derivative of trig yet. Sorry. I thought I cropped those off. You do, however, know how to do 3, 4, 5, and 6. Those are the old inverse derivatives using our formula. And then these are like what we did today. So the inverse tan of -1, what is that equal to? Okay. So sorry about that. Skip 1 and 2. So you're really doing 3 to 29.